Today is a seemingly normal day, maybe a quiet Sunday. A bright flash appears in the sky. It is not visible to the naked eye from the ground. It is seen by powerful telescopes. It is also detected by space surveillance networks. These networks use radar to track objects in orbit. The flash is a sign of a high-speed event. It comes from an object in low Earth orbit. The object was a newly deployed device, supposed to be a space mine. But something went wrong. The single object on tracking screens flashes and becomes a cloud of many smaller objects. This is the first visible result of a catastrophic failure. The mechanism is simple and violent. The device, meant to disable another satellite, destroyed itself. It was supposed to separate cleanly from its deployment stage. Instead, a failure occurred. Perhaps a pyrotechnic bolt fired incorrectly. Perhaps unused propellant in a tank ignited. The device's structure could not handle the force. It shattered. Energy from the failure sent pieces in many directions at immense speeds. They form an expanding cloud of lethal projectiles. The cloud is not static. It spreads out. Some pieces are pushed into slightly higher orbits. They slow down relative to the original object. They begin to lag behind. Other pieces are pushed into slightly lower orbits. They speed up. They begin to race ahead. Over hours and days, these small speed differences stretch the cloud. A tight cluster becomes a thin, dangerous ring of debris encircling the planet along that orbital path. This outcome is purely physical: momentum and energy. The device had a certain mass and velocity. When it broke apart, mass and momentum were conserved and redistributed among many fragments. Each fragment carries huge kinetic energy because of orbital speed. A 1-centimeter aluminum piece at 7.88 km/s has the destructive power of a hand grenade. The single failed object is now thousands of potential threats to other objects in similar orbits. What is a space mine? The term sounds like science fiction, but the concept is real. It's a device placed in orbit to interfere with or disable another satellite. It can be a small machine designed to cut a power cable, block a sensor, or create a localized cloud of debris. Deployed by nations or corporations for strategic advantage, these tools of control come with significant risks, from diplomatic fallout to the creation of uncontrollable orbital debris. The mine's failure is immediate. It fragments into thousands of pieces, creating a cloud of debris. Traveling at over 17,000 miles per hour, each piece becomes a projectile. At these speeds, a collision is a hypervelocity impact, an explosive event. A small fragment can shatter a solar panel. A larger one can destroy a satellite instantly, punching through its structure and rupturing fuel tanks. For the owner on the ground, the first sign is silence. The initial failure creates a feedback loop. A feedback loop is a cycle where the output of an action becomes the input for the next action. Debris cloud, satellite collision. More debris, back to debris cloud labeled increases collision risk. That debris then hits other satellites. When a satellite is hit by a piece of debris, it can break apart. That breakup creates even more debris. This new debris increases the total number of fragments in orbit. The increased number of fragments makes future collisions more likely. This cycle is the core idea behind a concept known as the Kessler syndrome. It is a cascade of failures. There is a threshold for this process. A threshold is a tipping point. Below a certain density of debris, collisions are rare and the environment is relatively stable. Satellites can operate safely for many years. If debris density crosses a critical threshold, the rate of collisions increases rapidly. The feedback loop becomes self-sustaining, generating debris faster than natural decay removes it. Once crossed, an orbital region can become unusable for a very long time. These effects do not appear all at once. There are significant delays. The debris cloud from the first failure takes time to spread and encircle the Earth. The first secondary collisions might not happen for months or years. That delay can create a false sense of security for operators, but the risk keeps growing silently. The probability of a collision is a statistical game. Over time, a collision becomes almost certain if debris persists. Operators' incentives change. Protect the asset. One choice: power down and put the satellite in safe mode when passing through dense debris. That protects the hardware but interrupts services like internet, or interrupts services like GPS. Another choice: use fuel to move their satellite to a different orbit. That avoids debris but uses fuel, shortens mission life, and can cost millions in lost revenue. A cascading failure permanently alters the space environment. Debris doesn't just disappear. At 400 kilometers, atmospheric drag pulls objects down in years. But at 800 kilometers, debris can remain for centuries, turning entire orbital bands into no-go zones. This forces changes in satellite design, adding shielding and fuel for avoidance maneuvers. The cost of doing business in space goes up for everyone, and the orbital environment becomes permanently more hazardous. After a major failure, incentives for all space actors shift dramatically. Satellite operators face hard choices: maneuver away from debris, costing precious fuel and shortening a mission's life, or risk their multi-million-dollar asset. Governments must decide whether to impose launch bans or new regulations that make space more expensive for everyone. The insurance industry reacts by raising premiums, potentially making some business models unworkable. Once a debris cloud is created, several actions can be taken to mitigate the damage. The first and most important step is tracking. Ground-based radar and optical telescopes are used to map the new debris field. The goal is to create a catalog of the largest fragments, tracking their individual orbits. This catalog allows satellite operators to receive warnings when a piece of debris is predicted to make a close pass. With enough warning, an operator can fire their satellite's thrusters to perform an avoidance maneuver, moving it slightly to get out of the way. However, tracking has significant limitations. Current technology can reliably track objects down to about 10 centimeters, the size of a softball, in low Earth orbit. The fragments that are most dangerous are often smaller than this. A 1-centimeter piece of debris is large enough to destroy a satellite, but it is too small to be consistently tracked and cataloged. This means that even with the best tracking systems, satellites are still flying blind against a large population of lethal but invisible threats. Operators can only avoid the large pieces they know about. A more active approach is to try to remove debris from orbit. Several concepts for active debris removal exist. These involve launching a special garbage truck satellite. This craft would be designed to rendezvous with a large piece of debris, such as a dead satellite or a spent rocket stage. It could then capture the debris using a net, a harpoon, or a robotic arm. Once captured, the ADR craft could fire its engine to push the debris into a lower orbit, where it would safely burn up in the atmosphere. These mitigation efforts are extremely expensive and slow. Developing, building, and launching a single ADR mission can cost hundreds of millions of dollars. One mission can typically only remove 1 or 2 large pieces of debris. Meanwhile, a single satellite breakup can create thousands of new fragments. The economics do not currently favor cleanup. It is far more expensive to remove debris than it is to create it. Because of the cost and complexity, no large-scale ADR missions have been deployed yet. We have the technology in theory, but we lack the economic incentive to use it at the scale required to solve the problem. The physics of orbital failure are clear, and engineering solutions for prevention and cleanup are understood. We can design safer satellites and track debris. But the fundamental problem isn't technical. It's about economics and responsibility. Preventing failures requires upfront investment. Cleaning up is even more expensive. The lingering question is, who should pay? For a single operator, saving on safety costs is tempting. But when everyone makes that calculation, the risk to the entire system grows. A classic tragedy of the commons. Should we create an international fund? Or adopt a stricter polluter pays policy? This choice will determine whether low Earth orbit remains a vibrant frontier or becomes a glittering junkyard. What scenario should we explore next? Share your ideas below. You've been watching Ifverse, where imagination meets possibility. See you in our next reality.